Jarrod McClean from Google AI, and we'll talk about post-supremacy quantum devices, practical applications.
Great. So thanks a lot for the invitation to come speak, and it's been a real pleasure to see all the talks so far and interact with everyone here. So my talk, I think, is going to be a different flavor of sorts than you've seen so far today. There'll be perhaps less algorithmic analysis and more kind of discussions of some of the challenges that we have in devices today for going towards applications of interest, perhaps not in a provable regime, but perhaps in a more heuristic one. So hopefully there's still something for everyone, and I'm happy to take questions if something isn't clear. But with that, let's move onward. So this is a slide that I like to show and say different things about depending on the audience. And it's kind of a fun graphic, not meant to be super accurate by any means, but it talks about the excitement about quantum computing as a function of time. And you might say that, it had some peaks and bumps along the way, say around the time that Shor's factoring algorithm came out, and a lot of three-letter agencies got scared, and people got very, very excited about these things. And you start to try to build these devices, and your excitement wanes a little bit, because it turns out to be incredibly difficult. In the more recent past, devices have been getting better and better, and our knowledge of, say, error correction and algorithms has also gotten better and better. And somewhere in the middle, I would say a confluence of things happened, but ultimately we had a few qubits that were good enough and a few ideas of how to use them that it seemed like it was no longer an impossible physics problem and more like an incredibly challenging engineering problem. And so at this point, excitement started to build and build, and devices have gotten better. A lot of industrial players have entered. The government's now put a lot of funding behind these types of projects, and we're building up and up and up. And this year, or I guess it was last year, our team announced this quantum supremacy experiment, which, as many of you know, was a big technical achievement, but really was aimed at designing a task that a quantum computer would be especially good at. So in a kind of hand-wavy sense, it was trying to find some task for which I could race a quantum computer against a classical one and show that it came out ahead in some serious way in terms of compute time. And so this was kind of the tenor of this, and along the way, it's basically a great integration test for a device that hopefully you get into this error-corrected regime. And so a lot of the algorithms that we've heard about so far, and a lot of the ones that we dream at, like Shor's, do live in this error-corrected regime, which assumes that we've, through redundancy, made essentially perfect qubits, and that we can do almost anything we want. But there's a question of whether we can start to do practical applications before we have these perfect error-corrected qubits. And this is sort of what I mean by using a post-supremacy device for practical applications. It's a device capable of running this race against a quantum or classical computer, doing some task, but now I'd like to ask, can it do more tasks that I'm interested in? And I think if we can really find even a few great examples here, it helps bolster our mission to get to error-corrected quantum computation in the sense that it excites people and finds new things. So this is kind of the area that I'm going to talk about primarily. So for us, I'll just put one slide up about the quantum supremacy result to show kind of what we're proud of in terms of our device error rates. There's, I guess, an entire week devoted to something like quantum supremacy later in this Simons Foundation, so I won't get too much into detail. But essentially for us, in addition to this nice race against classical computers, you can sit down and look at what are your 1 and 2 qubit error rates, not only for the isolated qubits on this 54 qubit device, but while running them all in parallel, which presumably, if you believe in things like crosstalk and engineering complications, is a harder task. And what you find, so since it might be hard for you to read, is simultaneous parallel operation single and 2 qubit gate error rates of about 0.2% and 0.6%. Respectively, and even lower kind of cycle error times, or even just above cycle error times. The readout was a bit not so as perfect, but it's something that we're hoping to fix quite soon and still quite respectable at around 4% error rate. So kind of this preface is to say that assuming you have such a device, one might consider 54 qubits with that kind of error rate to be something that you'd really like to play with. How do you start to use it effectively to make meaningful statements about progress towards applications? And what are these application areas? I'm going to talk about a few of them, but some of the ones we heard about today, this morning, in the QAOA and other optimization technique session So kind of these relation representations or quantum machine learnings using quantum neural networks we heard about yesterday. And of course, quantum simulation that I'll talk a little bit about today, simulating truly quantum systems like the nucleons inside of a nucleus, or perhaps atoms and molecules or their electrons. And these have these nice representation properties that we believe that it's sort of hard to represent very correlated quantum systems using classical systems natively. So what does it mean really to use a post-supremacy quantum device? So imagine that you have one over here. And my goal is to do is an interesting computation as close to classically intractable as possible. So what does that mean? What it doesn't mean is doing the largest possible experiment you can squint at and see a curve through. Fidelity and accuracy tend to matter, as we've seen in a lot of the other competitions between quantum and classical, that if your accuracy is not good enough, you can just do a kind of crappy mean field method, because remember, unlike supremacy, these problems are probably going to have reasonable structure. They're probably engineered by human beings who have been working with them for a long time, and we probably have decent methods to begin with. So if you're not good enough, you're probably going to get beat by a much simpler method. And my prediction, and I hope to substantiate this a little bit, is that doing an interesting simulation beyond 20 qubits will be extremely difficult without error reduction techniques, even if you have great fidelities. And so let me do a little back of the envelope calculation for you, one that can be easily followed if you'd like. So imagine that I have, say, a 20 qubit system that I'm interested in. I'm going to prepare the ground state of hydrogen, so you won't need to know anything about quantum simulation to follow this. I'm going to assume that I have a perfect gate sequence for this, and it's about depth 20. And so if I use my most naive fidelity estimate, and I just kind of product these all together, I get a respectable fidelity of about 80%. So if you did a 20 qubit experiment, depth 20, you'd probably be pretty happy with 80% on today's devices. What does that mean for my predictions that I would like to make? So hydrogen has a gap from the ground to the first excited state of about half a Hartree. And so if I just take that fidelity and I dump all of the error into my first excited state, so the most optimistic error that I could make rather than hitting the rest of the spectrum, I get an error that's about 0.1 Hartree, which, to give you a reference point, is around 1 or 2 orders of magnitude worse than I would like to do. And so this is both a too optimistic and too pessimistic estimate, because truly I care about energy differences rather than absolute energies, and you might get some correlated error cancellation. But the point is, even for this kind of small system, this is already kind of bordering on hard to interpret. And so today I'm going to talk a little bit about error correction and can it help us on NISC devices. Because I think there's a pervasive feeling in the field that sort of error correction is this thing that undergoes a phase transition in more ways than one, where it essentially hurts you dramatically for a very long period of time, and then when you cross this magical threshold, suddenly everything works perfectly. But I think the basic ideas of redundancy and kind of other things that are within it might still be useful in the near-term regime to help us discover more things about applications. And so just to kind of broaden it a little bit from only talking about quantum simulation, I thought an interesting version of quantum machine learning that hasn't been talked too much today, hasn't been talked too much yet, but one is this kind of quantum kernels that people use, where you try to do a classification problem and you divide up your system based on some complicated unitary. The idea being, say, if you have like a supremacy level device, you could do a very complicated circuit and make very, very intricate patterns that would be hard to classify for some sets of data on a classical device. But what I wanted to emphasize is that once you start to add noise, that sort of thing might blur some of these islands together, and a classical approximation might do just fine. So anytime you're talking about using one of these noisy devices on a real application, you have to be cognizant of the way noise changes your ability to approximate it more easily. And so there is kind of one point that I wanted to make that I haven't heard too much talked about. So everyone talks about using a quantum device to beat a classical one at some task, but I actually think there's a much more modest goal that we should strive for, which is, as many of you might know, some of our best provable performance computer science algorithms are not always the ones we choose to use in practice for various reasons. And so arguably one of my hopeful uses of an early quantum device is to learn what actually works well on a quantum device outside the regime that I can easily simulate classically. So a very simple example of this would be, imagine you had like the QAOA circuits you saw from this morning, and I'll introduce those a little bit more in a second. But I just have, say, on 50 qubits, some ansatz. And because it's variational, if I doubled it up, in principle, I should do a little bit better. And I'd like to know how much better I'm doing. But in practice, on a 50 qubit device with too much noise, I add more variational parameters, and my answer gets worse. Because the amount of noise I couldn't compensate for that. And so it becomes a question of, first, I would like a goal of at least being able to prove things about primitives or explore primitives that are not yet present. And then I can use that to help me get to this more lofty goal of how to use the chip to go beyond current classical results. And so hopefully some of the techniques that I'm going to talk about will be useful for this. So a lot of the algorithms that you've heard about already stem from this nice simple primitive of device-compatible implementations, which was often what you might talk about is given a task, and you can design a circuit to perform it that is hopefully optimal. You get your gate counts down, you get your complexity results down, and if everything works and it fits in your device, you get out 42, or the answer to life and everything. But if it doesn't quite go in, you might not get anything out. And so the alternative is, given the task and the current architecture, find the best solution possible by means of sort of iteratively updating these schemes. And there's a lot of course, algorithms that fit within this, and I'll talk about only a few. And so the idea of this is, of course, to use the quantum computer where it's needed, offload any kind of mundane computations that you might have onto a neighboring classical device that's well developed. And most of them follow a simple pattern, which is you're rewriting some optimization problem that you'd like as this minimization of some expected value of a quantum wave function. And you've seen many talks about this today, but essentially, you're going to have some inputs given by these coefficients, and you're simply going to ask your quantum circuit many times, what are the values of these Pauli operators? So this is a task that's quite easy for a quantum computer, given enough depth. And adding all of these together is, of course, quite easy for a classical computer. So you combine the two of these, and you get out one of these hybrid schemes, essentially. And so you've seen this in other contexts today, and I won't belabor it too much. But the idea is to simply use the quantum device as this object, which stores a very complicated probability distribution for you of sorts. And our belief in this, that it might be powerful, comes from supremacy-like arguments, of course, that we have such distributions that are hard to sample from, but of course using it is quite complex. And then I'm going to sample only a little bit of information from that, feed it back to my CPU, and try to do better and better. And this fits kind of in a lot of different problems. So in a nutshell, these are essentially problems, often which map between, say, eigenvalue problems and minimizations over some parameterization. And today I'm going to really focus on a different part of that, which is, apart from the numerous applications, which is, say, chemistry, nuclear physics, QAOA, as you heard about this morning, machine learning, is what happens in the presence of coherent and incoherent errors for these types of algorithms. Can we still learn about these primitives even if we have substantial noise? And so it's helpful, I think, based on people I've talked to here that perhaps have not seen an explicit example of this, to walk through at least one just briefly. So what does one of these experiments look like in practice? This is a kind of it's starting to age, but it's still a good experiment, of course. And if you just take 2 qubits, so I'm going to examine a hydrogen experiment, and I run my quantum circuit down here and just map up to exactly what's happening on my chips here. I have one parameterizable piece down in this Z rotation. I'm going to measure my different operators and then just feed back, and hopefully through the optimization of this, get a better and better approximation to the ground state. And so what's the result of this? So what this graph is if I take my 2 hydrogen atoms and I rip them apart, what is the energy as a function of that pulling apart? And I'm doing each one of these problems separately. So this variational quantum eigensolver experiment that I talked about is the parts in red, and the parts in blue are the attempt to do that with the same system with a phase estimation experiment. And so if I'm recalling correctly, we had actually hoped at the outset of this that the device was good enough that the combination of majority voting error correction on the phase estimation would bring us better than the variational result. But what we found was that was not really the case. And we wanted to dig deeper into why this was actually happening. And what we found is, of course, that because this thing is only 2 qubits, I can go back and tell you exactly what this angle theta should be in the ideal case. It's not too hard. and then I calibrate my device as best I can. I plug that angle in, and I see what happens. And that particular calculation, or that particular sequence of events, what you get is all of these green dots. And what you do if you do this variational loop is the red dots. And so in some ways, this optimization loop is performing, say, an on-the-fly calibration, since it doesn't really care about what the labels on your angles are, but it's able to just update and kind of correct for things that were hard to see in a kind of fully integrated experiment for just calibration. So that leads us to believe that we're at least a little robust to certain types of errors, which are sort of calibration-like or over-rotation errors, so that makes us feel pretty good about that. But this is not the type of error that one might be most concerned with. So we started some work even while I was here at LBNL on going beyond this ground state without more qubits or gates. And so the original hope was actually to go and get excited states, which we did. But imagine you're in a situation where you've already done this and you have some great reference wave function. And I would like to do only additional measurements on that. I'm going to build up a classical generalized eigenvalue problem. So once again, one of these quantum classical kind of couplings. And from the solutions of this generalized eigenvalue problem, I'm going to give you not only excited states, but a lot more at the same time. So I'll walk you through sort of how this works and the results you get. But then I'm going to have to take a little bit of a detour into error correction to tell you why it does what it does. So what is the general idea of this sort of subspace expansion that we're going to perform? And the hope is to learn the action of the Hamiltonian in a subspace around the state that I've prepared. So what do I mean? If I've done my variational calculation successfully across this nice manifold, and I've found this point, which is an optimum here, then I would like to learn things about how the Hamiltonian acts on my system sort of around that state without knowing any detailed knowledge of my actual state itself. And I can do this by introducing a set of operators O that are going to sort of act and probe on this space. So I'm going to act my Hamiltonian on this O, which acts on the state, and probe with the same set of states. So if you're more of an applied math bent, this sometimes goes by a name like Galerkin approximation, but it's nice because it creates this closed dynamics in a subspace. And so if I take care of all the other parts correctly, at the end of the day, I'm set up with this matrix equation that's offline. So I've measured all of these matrix elements individually. And I've written this in a suggestive way, which is to say that rather than perform these O's, which I'll tell you what they are and how to pick them in a second, I'm actually just dressing my Hamiltonian with these O's beforehand and changing the measurements that I do on the states that I prepare. So in that way, up to usually kind of individual rotations, I don't make my circuit any longer. I still keep the same amount of quantum resources. So something happened that was a little bit surprising. We were able to show an experiment. So this is the plot of the error versus the distance for the same type of molecular curve, but now an experiment we did with Irfan Siddiqui. And in fact, we'd made a little bit of a prediction in this in the theory paper, but the reviewers told us that they didn't believe us and we needed an experiment. And what they didn't believe was, so these different lines are each different collections of those expansion operators O I mentioned. So I, being the identity, is just the original VQE result. And as I added more of these operators, and keep in mind this is kind of a way of taking measurements that I do incoherently and finding a way in which they would coherently add in principle, I'm able to remove the remaining error of my system, sometimes by a few orders of magnitude even. And so if we believe that this VQE result also took care of the coherent errors, then it looks like a lot of what's been removed is the incoherent errors. So how can you do that with kind of this just incoherent averaging in an offline eigenvalue problem? So this was a little bit of the mystery that led me down a path towards a bit more quantum error correction. So I'm not going to talk in too much detail about quantum error correction. I find people sit in one of two camps within quantum computing, which is they're either absolute experts and know everything that's about every decoder that's ever been written, or they assume that's someone else's problem and they're waiting for the logical qubits. So I'm going to tell you just enough to kind of get the picture of why this result works and how we might start to import tools from quantum error correction that might still be useful for us. So how does classical error correction work at a glance? It works through some combination of redundancy and a reasonable model of errors. So you can imagine that if you encode redundantly a 0 is 3 zeros, a 1 is 3 ones, and assume that single bit flips are probably more likely than all of them moving at the same time, then a simple scheme like majority voting can allow you to correct errors. And of course, there is a long history of quantum error correction where, due to no cloning theorems and measurement destroying information, people thought that perhaps this wasn't possible. But luckily, as you all know, it now is. And the trick is to use redundancy in the form of symmetries. So I'm just protecting against bit flip errors here. But instead of this kind of basic redundancy of bits that I had before, I'm going to encode it into some subspace of the symmetries which I choose. And I'm going to choose them such that they protect me against my reasonable model of errors, which is usually that local errors are much more likely than global errors. And if I'm successful in measuring these symmetries, it does not, in fact, destroy my information, and I'm allowed to recover my information in that regard. So a sketch of the type of code that I'm talking about. So they're often referred to as stabilizer codes, where the stabilizers are these symmetries that I've engineered into my system. In the ideal case, you're in this nice blue code word space. An error takes you out. You detect it and recover. If you take too many errors, you might get a logical error, which takes you into another blue state by accident. And if you're doing a logical operation, you want to purposefully move between these states. So you often just choose a commuting set of poly operators. Denote this as the stabilizer group. You define the code words, or nice parts of this blue space, to be the +1 eigenstates of these operators. So for example, for the repetition code, the operators which generate this are these. And then, of course, you'll have logical operators. So you might have just been able to see by inspection that applying 3 x's to this 0 state will then give you the 1 state. Doing more interesting operations is, of course, quite an endeavor when you're in more complicated codes. But for the purposes of this is about all you'll need to know. So how does error correction work in some sense? So in a very broad sense, you'll need to do some measurement of these syndromes after an error, and then you recover the state as quickly as possible. But if you're working more in the near-term regime and you say, well, it's not as important to me to do this type of operation, maybe I'm OK with just dramatically reducing the error rate, even if it's not quite scalable yet, and I can start to borrow things from the scalable regime. So if you were to take a different point of view, maybe the only thing I'd really like to do is to say it's more likely that or it's not so likely after a short amount of time that I've taken on these logical errors. So most of what I want to do is just remove this space and focus only on things that have remained in the correct subspace. And so you can do this by just constructing projectors from those symmetry generators that I mentioned before. And the advantage of doing it in the way I'm about to describe, which you might not see the details of yet, is that it will tend to reduce errors considerably for small experiments. It allows you to use a device in the lab today to test code properties, even if the code has fairly non-local stabilizers. And it's like error detection, but without explicit stabilizers, and you can explore some recovery channels in this way. So to make one clear distinction before everyone always asks, the difference between this and post-selection is actually that I'm not going to measure the stabilizers explicitly. I'm going to measure only transversal operators and average out the space in a somewhat indirect way, but hopefully one that you'll see is quite experimentally interesting. So how do we do this? Just to remind you how these projectors work. So if I use this projector for symmetry SI, and I've hopefully engineered it so that common errors E anti-commute with it, then this projector will remove any component of a wave function that's had that error applied to it. And kind of the projected density matrix version of this is just that you get this sort of renormalized density matrix. And so what we're going to do is actually not recover the quantum state. My goal instead is going to be that I often only want some nice observable, like an energy of a system or a kind of its spin magnetization. And all I'm going to ask for is that I'm going to get a better averaged value for some operator A than I could before. And the way I'm going to do it is I'm simply going to re-express this as this kind of incoherent sum that you've seen before over all of these operators within the projector. And the important caveat here is that it's over only these kind of transversal poly operator measurements. I never have to attach ancilla and do true syndrome measurements, which tend to kill so-called pseudo-thresholds because of the way they soak up errors. And you might be looking at this and say, huh, doesn't that look like it contains an exponential number of terms in it? Aha, I've got you. Well, you'd be right, but you wouldn't be right quite correctly about the scaling yet. Because we've chosen these things to be in the +1 eigenspace by their construction, in fact, if there's no errors in the state, this operation of kind of going through a loop and choosing a random polyframe at the end of the determined by these symmetries does not actually affect the statistics of measurement if my state is perfect. So I need to do the same number of repetitions in this wonderful ideal case. And as I lose fidelity, some of those symmetries start to flip, and I get sort of a plus-minus effect that then averages out the incorrect parts of my space. So I can do this essentially without needing any extra control qubits and on any real code that I want, assuming that I've managed to prepare the initial state. And so this is kind of the trick that we're going to use to implement near-term error correction in a way. So you might say, well, that was a nice story, but didn't you say something about a generalized eigenvalue problem? Can you get back to that? So suppose that you don't know the symmetry subspace, or that the problem has a logical Hamiltonian as well, where you prefer some code states over others. So if I rewrite this as some general projector where I get to choose the weights, and then I'm going to minimize over these coefficients, where my Hamiltonian will be the Hamiltonian of my code space. It goes up in energy if I break or violate one of my nice symmetries. And I'd like to subject it to being like kind of a actual quantum state. And so you might look at that for a second. And if you've done a bit of chemistry in the past, you'll immediately know the exact solution to this equation. If you haven't, you might have to think about it a little bit. And it'll be exactly the thing we wrote down before. This generalized eigenvalue problem solves this particular instance exactly. So we had essentially intuited a way to get the right projectors, and this was the effect that was happening is we were learning code space projectors that were inherent in our system, and this was removing additional noise in our experiment. So how does this work in practice? I'll just close a few quick examples. So we wanted to just evaluate how good does a device need to be, at least in the best possible case, to start seeing benefits from this type of procedure. Because you might be thinking in your head that you've heard of thresholds and pseudo-thresholds in the order of like 10 to the minus 5 for error rates. And so maybe this is still not useful. So we looked at the 513 code, which means 5 physical qubits comprise 1 logical qubit with distance 3. And we looked at first recovery only in sort of this memory model. And we set each of our 5 qubits to have a depolarizing channel on it with some probability p. And you only need to pay attention to the lowest line for the purposes of this versus this bare physical qubit, which was what would happen if this was just a single qubit getting that depolarizing channel. And we shockingly found a pseudo-threshold of up to 50% depolarizing on each of the individual qubits, which is to say if you have any error below that, which most devices of ours do, of course, you get a substantial benefit from this encoding. So this is, of course, just recovery on a very simple model, but it gives us a nice kind of guess that these techniques might be more applicable than we might have thought in the near term. So another quick example, in course you don't have enough qubits to afford a different encoding, is that sometimes you have these symmetries naturally in addition to the ones you might engineer in your system. So for fermionic systems, we know we have spin symmetries and other things like that. And you can even focus on easier symmetries that you might be interested in. And in these cases, there's no reference. It's just always beneficial to invoke one of these kind of symmetry projections to help your system out. So I think I'm reaching near to the end of my time, so I will just quickly summarize by saying that we think that even with a great device, it's going to be pretty challenging to simulate some of these systems, and it's going to be even challenging to create experiments where I learn how to do better application quantum experiments. And what I hope to have at least told you, not only about the technique that we worked on and we have hope for, but just to give you all hope that there are ideas from error correction that are going to be a lot more powerful, I think, in the near term than we might have given them credit for originally. As we start to introduce more aspects of error correction in a more heuristic way, I'm hopeful it's going to let us bring down errors in a new and interesting way, and that there might be more before this crazy error correction transition. So with that, I'd like to thank all of my collaborators that helped me with this work and all of you for listening. Thanks a lot. Questions?
Do you think that there's any, so if you identify a symmetry in a fermionic Hamiltonian, you can try to remove it by adjusting your mapping, or you can use the technique you're describing. Do you think there's any benefit And there's a case where you're better off actually using it for this type of correction rather than just removing it using like a more aggressive mapping?
Yeah, so great question. So we've actually seen in a fair number of cases, so people have attempted to remove these symmetries manually from the Hamiltonian. Often what you get out is fewer qubits, which is nice, but a dramatically increase in complexity in the Hamiltonian itself, or in some cases in the representation. And so when you kind of trade off the increased complexity of the gates and like things that you have to do, you find that sometimes it is still beneficial to use the simpler but more redundant encoding, and then especially if you then use the symmetry corrections on top of it. I'm sure there's instances where this is not the case, but we've seen a few where this is still the way to go, basically. Thanks. Yep.
So you mentioned at the beginning of your talk that the readout error is the kind of most significant type of error that you have.
Yep.
And the error correction schemes that you proposed rely heavily on measurements.
Yeah.
So I was wondering how much this very significant readout errors impact the error correction schemes that you have.
So for these schemes, so that has a big impact, of course. It's actually interesting that in fault-tolerant error correction for the surface code, despite its heavy dependence on measurement, it is a little more it's a little more robust to that type of error. I think you can tolerate up to, say, 1% error in the measurement, whereas your gates need to be a little bit more precise. But you're right in that we are making an attempt in a great way to bring down that measurement error, but in fact, the basic redundancy helps us with our measurement errors even more so in some cases than our gate errors. So yes, there is this compounding effect, but the fact that you can kind of majority vote away, even if you use a very basic like repetition code, your measurement flaws, you still tend to come out ahead. But I'd say in the long term, we definitely want that measurement error reduced greatly from what we have today.
How do you select these operators O in order to get the generalized eigenvalue problem?
So when you're doing the generalized eigenvalue problem version, you do have to, rather than doing it stochastically like we did before, you do have to select them. So when it kind of is problem dependent, I would say, because you're a little bit more constrained by the number that you're going to do. When we did excited states, the choices were natural for fermions, which were single fermion excitations. When you're trying to do it for error correction, we basically, the ways in which we did it were we essentially would choose stochastic samplings from that and then kind of optimize on top of it. So it was not a perfect procedure, but yeah, I guess this is kind of the combination of the two if you're interested in excited states and error correction, but it is difficult in general to pick out exactly the right stabilizers from this massive sum. So, thanks.
How did the Google hardware and its like crosstalk either help or hurt the error correction, in your opinion?
In talking, so I'm not the right person to ask about the details of our crosstalk. I have been told that our crosstalk is incredibly low compared to other architectures. Of course, if you have large correlated errors, this will just create a greater density of errors. And for methods that are implementing full kind of surface code error correction, I believe there's results which say that it's not really the correlated errors that kill you, it's simply the raw density of errors. So if those correlated errors are much less likely than the kind of local errors, it won't matter too much. But of course, generally we just need to bring those types of fidelities down. As far as I can tell, if you're doing active measurements, those aren't particularly bad, except in the case when you have too many.
Thanks for all the questions, and let's thank Jarrod again.